In the deepest layers of Earth's memory, where stone keeps secrets and time moves like ancient rivers, something extraordinary may be waiting to rewrite everything you thought you knew about human history. What if the footprints of a civilization far more advanced than our own lie buried beneath millions of years of sediment, their technologies so sophisticated they dissolved back into the elements that birthed them? Tonight, we journey into the possibility that you are not the first to gaze at the stars and wonder about your place in the cosmos, but perhaps the inheritors of wisdom so profound it vanished without a trace, leaving only whispers in the geological record of a world that once knew secrets we're only beginning to rediscover. What if the most profound archaeological discovery in human history lies not in golden tombs or ancient cities, but in a single grain of sand that carries the memory of civilizations so old they predate our species by millions of years? In the sedimentary layers of Earth's memory, time moves with a patience that makes human consciousness feel like lightning, each stratum of rock representing millions of years compressed into inches, holding fossils of creatures that ruled ancient worlds and then disappeared into geological silence. These layers stack like pages in the universe's most ancient library, where every grain tells a story spanning eons, and where the history of intelligence itself might be written in languages we're only beginning to learn to read. Within these layers, scientists search with the dedication of cosmic detectives, seeking traces of intelligence that extend far beyond the familiar bones of dinosaurs or the scattered remains of early mammals. They hunt for the subtle signatures that advanced civilizations might leave behind, not the obvious monuments or artifacts that human archaeology recognizes, but the whispered evidence that speaks in isotopes and minerals, in chemical fingerprints and crystalline structures that defy natural explanation. The geological record spans an almost incomprehensible 4.6 billion years, stretching back to when Earth was a molten ball spinning in the cosmic dark. Yet human industrial civilization represents only the tiniest fraction of this vast timeline, a mere 200 years out of billions, like a single heartbeat in a lifetime of dreams. This perspective reveals a humbling truth. If intelligence is not unique to humanity, then vast epochs of time existed when other forms of consciousness might have flourished, built great works, and ultimately surrendered their achievements to the patient recycling mechanisms of geological time. If another intelligent species had risen and fallen during Earth's deep past, perhaps when the continents held different shapes and the sun burned with younger fire, their traces might exist in forms barely recognizable to modern archaeological methods. Traditional archaeology searches for pottery shards and foundation stones, but such materials crumble to dust across millions of years. Instead, the evidence of ancient intelligence might survive only in the language of chemistry and physics. Stone tools weather away under the relentless assault of wind and water, but certain isotopic signatures tell different stories entirely. These atomic fingerprints resist the erosion of time, preserving information about nuclear processes, industrial activities, and technological achievements in forms that can persist across geological ages. Unusual mineral concentrations might mark the sites where ancient smelters once burned, while rare earth elements found in unexpected configurations could signal technologies we haven't yet imagined. Perhaps most intriguingly, artifacts made from nearly indestructible materials, synthetic diamonds, crystalline matrices, or exotic alloys designed to outlast mountains, could wait patiently in the earth for future civilizations to uncover them. These materials would speak not in the familiar vocabulary of bronze and iron, but in the eternal language of atomic structure and molecular bonds that time cannot easily break. The whispers of deep time carry another profound implication. Intelligence may have emerged and vanished multiple times throughout Earth's history, each iteration rising from different evolutionary paths and achieving technologies that followed completely different principles from our own. While we built our civilization on metals and combustion, ancient intelligence might have mastered biotechnology, crystalline computing, or energy sources that left no carbon signature in the geological record. These ancient civilizations might have lived for millions of years, timeframes that dwarf human history, before succumbing to cosmic catastrophes, evolutionary transitions, or perhaps even successful transformations into forms of existence we cannot yet comprehend. Their legacy would remain buried in Earth's ancient layers, waiting for archaeological techniques sophisticated enough to recognize intelligence expressed in unfamiliar forms, leaving only the faintest traces for future civilizations to discover through methods we're only now beginning to develop. The search for these deep time whispers transforms geology into poetry and archaeology into cosmic detective work, where every unusual rock formation becomes a potential message from the deep past, and where the patient accumulation of sediments might conceal the greatest discovery in the history of consciousness. Proof that intelligence has written its story across Earth's history in chapters we've only just learned to read. Two brilliant scientists looked at Earth's geological record and asked a question that would challenge everything we believe about human uniqueness. If another advanced civilization had thrived on our planet millions of years ago, how would we recognize their existence today? This revolutionary question emerged from the brilliant minds of astrophysicist Gavin Schmidt and astrobiologist Adam Frank, two researchers who dared to approach humanity's most sacred assumption with cold scientific logic. They named their theoretical framework the Silurian Hypothesis, borrowing from those fictional ancient reptiles in Doctor Who, but their work represents something far more profound than entertainment. It represents a complete reimagining of how we search for intelligence in Earth's deep past. The mathematical framework they developed reveals a truth so startling it forces us to reconsider everything we thought we knew about preservation and time. Even the most technologically sophisticated civilization that ever existed, one that might have built cities touching the clouds, mastered energy sources beyond our imagination, and achieved complete harmony with their planetary environment, could vanish so completely from the geological record that we would never suspect they had ever existed at all. This erasure happens not through some cosmic catastrophe, but through the patient, relentless operation of geological processes that treat the greatest technological achievements as temporary arrangements of matter destined for recycling. Time becomes the ultimate eraser, working with such thoroughness that it leaves no obvious trace of even the most magnificent civilizations. Consider the fate of organic materials, the foundation upon which all biological civilizations must build. Every book ever written, every work of art ever created, every preserved record of thought and achievement would surrender to the inexorable chemistry of decay. Bacterial action dissolves complex organic molecules back into simple components. Oxygen combines with carbon to create gases that disperse into the atmosphere, and the accumulated knowledge of entire civilizations returns to the basic chemical building blocks from which it emerged. The bones and shells that populate our museums represent miraculous exceptions to this rule of organic destruction. They survive only when extraordinary conditions, rapid burial in oxygen-free sediments, mineral replacement, or preservation in extremely cold or dry environments, intervene to halt the normal processes of decay. For every fossil we discover, millions of organisms vanished without leaving any trace whatsoever in the geological record. Metals face an equally inevitable destiny in Earth's recycling system. The bronze that once formed ceremonial vessels transforms into green patina that eventually dissolves into groundwater systems. Iron becomes rust that disperses as microscopic particles through soil and rivers. Even modern stainless steel alloys, designed for maximum durability, would succumb to chemical processes operating across millions of years, their atoms migrating through countless chemical transformations until nothing remains of their original technological purpose. Perhaps most humbling, even the massive stone monuments that seem permanent on human timescales would eventually disappear under the patient assault of geological forces. Mountains themselves rise and erode away like waves in extremely slow motion. Tectonic plates carry continents through collisions and separations that would pulverize any architectural achievement. Wind and water work with geological persistence to reduce the grandest structures to sand grains that eventually find their way to ocean floors or get incorporated into new rock formations. Yet within this seemingly total erasure, the Silurian Hypothesis identifies potential pathways for technological signatures to survive across deep time. Rare earth elements, those exotic materials essential to modern electronics, might accumulate in unusual concentrations around ancient industrial sites. These chemical fingerprints could persist in rock layers long after every physical artifact had disappeared, creating geological anomalies that might indicate technological rather than natural processes. Nuclear technologies would leave even more persistent signatures in the form of isotopic anomalies, permanent alterations to the natural ratios of radioactive elements that could remain detectable across millions of years. The atomic signatures of nuclear reactors, weapons, or exotic energy sources would speak in the universal language of physics, creating time-resistant markers that no geological process could completely erase. Most intriguingly, truly advanced civilizations might have deliberately created materials designed to survive geological timescales. Synthetic diamonds encoded with information, crystalline storage systems built to last millions of years, or exotic alloys specifically engineered for deep time preservation could theoretically carry messages from ancient civilizations to their distant successors. The Silurian Hypothesis makes no claims about whether such civilizations actually existed. Instead, it provides rigorous scientific criteria for recognizing them if they had, transforming speculation into testable scientific methodology. This framework gives researchers concrete tools for distinguishing between natural geological processes and potential traces of prehistoric technological activity. The implications extend far beyond archaeology into fundamental questions about intelligence, technology, and our place in cosmic history. If technological civilizations could arise and vanish so completely that we would never detect them without sophisticated analytical techniques, then Earth's history might contain multiple chapters of intelligence that we have never imagined. This possibility transforms every unusual geological formation into a potential archaeological site, every chemical anomaly into a possible technological signature, and every mysterious pattern in the rock record into a potential message from civilizations that might have achieved wonders we can barely comprehend before vanishing into the patient amnesia of geological time. Buried deep within ancient rocks lies a chemical mystery that could rewrite the entire story of intelligence on Earth. Carbon atoms carrying atomic signatures so unusual that some scientists wonder if they might be the fossilized breath of civilizations that vanished millions of years before the first human ancestor stood upright. These molecular witnesses tell stories with extraordinary precision, creating chemical fingerprints that preserve the intimate details of ancient atmospheres, forgotten climate systems, and biological processes that operated when Earth bore a face unrecognizable to modern eyes. Each carbon atom locked within sedimentary layers carries information encoded in its atomic structure, a permanent record of the chemical environment through which it traveled during its journey through deep time. Carbon isotopes function as nature's most meticulous historians, recording events across millions of years with the reliability of atomic physics. The ratio between carbon-12 and carbon-13 preserved in sedimentary rocks provides scientists with an extraordinary window into past climate conditions, ocean chemistry, and the global carbon cycle as it existed throughout Earth's history. These ratios fluctuate in patterns that reflect the complex interactions between atmospheric carbon dioxide, marine chemical systems, and biological processes that have shaped our planet's carbon budget across geological ages. Within this vast isotopic library, researchers have discovered something deeply puzzling. Some scientists have identified unusual carbon isotope excursions in the geological record, dramatic, sudden shifts in atmospheric carbon composition that don't match the expected patterns from known natural processes. These anomalous signatures show rapid changes in atmospheric chemistry that mirror, in disturbing detail, the patterns created by modern industrial civilization as it burns fossil fuels and transforms raw materials on a planetary scale. The implications of this discovery ripple through both chemistry and archaeology, suggesting that the carbon cycle itself might serve as an archive of technological activity stretching back across deep time. Modern fossil fuel combustion creates distinctive isotopic signatures that will persist in sedimentary layers for millions of years into the future, serving as permanent chemical monuments to humanity's industrial age. When we burn coal, oil, and natural gas, we release carbon carrying specific atomic fingerprints that reflect both the organic origins of these fuels and the geological processes that created them over millions of years. Industrial processes beyond energy production also leave their own distinctive marks in the global carbon cycle. The production of concrete generates unique isotopic patterns as ancient limestone transforms into modern building materials through high-temperature chemical reactions. Steel manufacturing creates carbon signatures that reflect the complex chemistry of metal purification and alloy creation. Even the production of plastics and synthetic materials introduces artificial carbon compounds into the environment, creating molecular fossils of technological activity. The remarkable persistence of these chemical fingerprints means they could survive in sedimentary deposits for millions of years, creating permanent archives of industrial activity that would outlast any physical artifacts, architectural monuments, or technological devices. While organic materials decompose and metals corrode away to nothing, isotopic signatures remain locked within rock matrices with the patience of geological time, waiting for analytical techniques sophisticated enough to decode their chemical messages. The search for ancient carbon anomalies pushes the boundaries of analytical chemistry and isotopic measurement, requiring scientists to distinguish between dramatic natural variations and potential signatures of prehistoric technological activity. This detective work demands extraordinary precision, as researchers must separate the chemical effects of volcanic eruptions, asteroid impacts, and biological innovations from patterns that might indicate industrial processes operating in Earth's deep past. Massive volcanic eruptions can inject enormous quantities of carbon dioxide into the atmosphere, creating isotopic excursions that persist in the geological record for thousands of years. The carbon released from volcanic activity carries distinctive signatures that reflect the deep crustal and mantle sources from which it originated. Similarly, major asteroid impacts can alter atmospheric chemistry through the vaporization of carbonate rocks and organic materials, creating temporary but dramatic shifts in global carbon isotope ratios. Biological innovations throughout Earth's history have also created permanent changes in the carbon isotope record. The evolution of photosynthesis fundamentally altered atmospheric chemistry, while the emergence of organisms that build carbonate shells changed how carbon cycles between ocean and atmosphere. These biological revolutions created lasting signatures in the carbon isotope record that scientists must carefully account for when searching for potential technological traces. Yet, even after considering all known natural processes, certain carbon isotope patterns in the deep geological record remain enigmatic. Some ancient periods display isotopic signatures that don't quite match the expected patterns from volcanic activity, biological changes, or impact events, creating what geochemists call carbon mysteries that challenge our understanding of ancient atmospheric chemistry. These chemical puzzles raise profound questions about the possibility that some unusual carbon signatures might record industrial activities from prehistoric civilizations that operated according to principles completely different from modern technology. Such ancient societies might have developed biological carbon processing, atmospheric engineering, techniques or energy sources that created isotopic fingerprints unlike anything in our current industrial experience. The carbon isotope record thus becomes a form of atmospheric archaeology, where the chemical composition of ancient atmospheres preserved in sedimentary rocks might contain the fossilized signatures of technological activities that operated when continents held entirely different configurations and life followed evolutionary pathways we can barely imagine. In this molecular detective story, every unusual carbon pattern becomes a potential clue to industrial civilizations that might have flourished and vanished, leaving only their isotopic breath as testimony to achievements that preceded human technology by millions of years. The search for these chemical ghosts continues with increasingly sophisticated analytical techniques as scientists develop new methods for reading the carbon stories locked within ancient rocks. Each unusual isotopic signature discovered adds another piece to the puzzle of whether Earth's carbon cycle might preserve evidence of multiple technological civilizations that rose and fell across the vast expanse of geological time. Beneath the towering peaks of every mountain range on Earth, an extraordinary possibility lies waiting, Entire cities built by ancient civilizations might rest in perfect darkness, buried under kilometers of rock and time, their architectural wonders preserved in geological tombs that have kept their secrets for millions of years. This haunting possibility emerges from understanding how erosion works across geological time, operating with relentless patience to wear away mountains and fill valleys with sediment in cycles that span millions of years. The forces that shape Earth's surface follow no regard for the achievements of intelligence, treating the greatest architectural marvels as temporary arrangements of matter destined for burial beneath accumulating layers of rock, soil, and time. The Himalayas, those magnificent peaks that seem eternal from human perspective, represent relatively recent geological formations that began rising only 50 million years ago. The Andes, stretching along South America's western coast, are even younger in geological terms. These major mountain ranges could easily conceal evidence of ancient settlements that existed before their dramatic upward thrust, hiding entire civilizations beneath their rocky foundations like geological filing cabinets, storing the achievements of forgotten worlds. Consider what this process might have accomplished across deep time. Ancient cities that once spread across vast plains could now lie entombed beneath mountain ranges, their streets and plazas crushed under the weight of tectonic forces that lifted entire regions thousands of meters above their original elevations. River valleys that once harbored thriving civilizations might now rest deep within mountain cores, their urban landscapes compressed and preserved like flowers pressed between the pages of stone books. Advanced ground-penetrating radar and seismic imaging technologies occasionally reveal tantalizing glimpses of what lies beneath our feet, unusual subsurface structures that don't match any known geological formations. These instruments send electromagnetic pulses and sound waves deep into the Earth, creating three-dimensional maps of buried features that challenge conventional explanations and spark intense speculation about their origins. The anomalies discovered through these techniques display characteristics that seem almost impossibly artificial. Straight lines extending for kilometers through solid rock, perfect right angles buried at depths where natural processes should have created only irregular formations, and geometric patterns so regular they appear designed rather than randomly formed by geological forces. These subsurface mysteries exist far below any known archaeological sites, in regions where conventional wisdom suggests only natural rock formations should exist. Recent archaeological discoveries provide sobering reminders of how easily significant achievements can remain hidden until accidental discovery brings them to light. Göbekli Tepe in Turkey, now recognized as the world's oldest known temple complex, lay buried under artificial hills for over 10,000 years before excavation revealed its sophisticated stone circles and intricate carvings. The site challenges assumptions about the capabilities of ancient peoples and demonstrates how easily major archaeological treasures can remain concealed. Similarly, underwater structures discovered off the coast of Japan display architectural features, stepped platforms, right-angle cuts, and geometric arrangements that some researchers interpret as evidence of human construction rather than natural rock formation. These submerged anomalies raise questions about how sea level changes and geological processes might have concealed other significant archaeological sites beneath modern oceans and coastal regions. If technologically advanced civilizations existed tens of millions of years ago, as the Silurian Hypothesis suggests might be possible, their ruins would likely be buried far deeper than any conventional archaeological excavation could reach. These ancient cities might rest beneath kilometers of accumulated sediment, accessible only through accidental geological processes that occasionally bring deep materials to the surface. Mining operations sometimes encounter anomalous structures, or materials at depths where they shouldn't exist according to conventional geological models. Earthquake fractures occasionally expose deep rock faces that display unusual features, patterns that seem too regular to be natural, materials that don't match surrounding geology, or voids that suggest artificial rather than natural cavern formation. Volcanic activity can sometimes bring deep buried materials to the surface, offering rare glimpses into geological layers that normally remain forever hidden. The possibility that entire metropolitan areas from prehistoric civilizations rest beneath modern landscapes transforms our perception of familiar geography. Every mountain range becomes a potential archaeological treasure house, every sedimentary basin a possible repository of architectural wonders that surpass anything in recorded history. The rolling hills of agricultural regions might conceal the foundations of cities that once rivaled or exceeded modern urban achievements. This hidden archaeological potential adds profound mystery to landscapes that seem thoroughly familiar and explored. The mountains visible from any major city might contain within their geological cores the preserved remains of ancient metropolises whose inhabitants achieved technological mastery along pathways completely different from human development. Their building techniques, urban planning principles, and architectural aesthetics might represent approaches to civilization that we cannot yet imagine. Advanced civilizations operating millions of years ago might have preferred underground construction, building extensive subterranean networks that would naturally survive surface catastrophes and geological changes. Their cities might have been designed from the beginning to exist primarily below ground, creating underground urban environments that continued to function even as surface conditions changed beyond recognition. The tools needed to explore these possibilities remain at the cutting edge of technology. Deep core drilling projects occasionally encounter unexpected voids, unusual materials, or structural anomalies that challenge geological expectations. Space-based gravitational mapping can detect mass anomalies that might indicate large artificial structures buried deep within mountain ranges. Advanced seismic tomography creates increasingly detailed images of subsurface features that might reveal geometric patterns inconsistent with natural formation processes. Each unusual subsurface discovery raises questions that challenge conventional understanding of Earth's history and the development of intelligence. The mountains that frame our horizons might conceal architectural achievements that would revolutionize our understanding of what consciousness can accomplish when given sufficient time to develop technologies we have not yet imagined, leaving their greatest works buried in the patient darkness beneath peaks that have kept their secrets across millions of years of geological time. Every plastic bottle discarded today will outlive human civilization by millions of years, creating an unexpected window into one of archaeology's most profound questions. If our synthetic materials can survive geological time, what imperishable artifacts might ancient advanced civilizations have left buried in Earth's deepest layers? This startling realization emerges from understanding the true lifespan of modern, synthetic materials which resist decomposition with a persistence that would astonish their original creators. While organic materials surrender to bacterial action and metals succumb to oxidation across thousands of years, plastics and engineered polymers represent something entirely new in Earth's history, artificial materials designed with molecular structures so stable they could persist virtually unchanged across geological timescales. Modern civilization has inadvertently created materials that will serve as permanent markers of our technological age, forming what scientists call a technosphere layer in the geological record. Synthetic polymers, engineered ceramics, and artificial compounds designed for durability have introduced molecular structures that never existed in nature's 4 billion year history of chemical innovation, creating substances that biological decomposition processes cannot effectively break down. These materials resist the very mechanisms that erase most evidence of past civilizations. While wood rots, paper dissolves, and even bronze corrodes away to nothing, plastic polymers maintain their molecular integrity through chemical bonds that remain stable under the temperature and pressure conditions found in most sedimentary environments. The same properties that make plastics useful for modern applications, resistance to moisture, chemicals, and biological attack, also ensure their preservation across deep time. The implications for understanding ancient civilizations prove profound when considered through this lens of material persistence. If modern synthetic materials can survive millions of years, then hypothetical advanced civilizations from Earth's deep past might have developed their own imperishable substances, artificial materials designed either intentionally or accidentally to outlast their creators and serve as permanent testimony to their technological achievements. The search for such ancient synthetic materials pushes archaeological chemistry into uncharted territories, requiring sophisticated analytical techniques to distinguish between natural polymers created by biological processes and artificial compounds manufactured by intelligent design. This chemical detective work demands instruments capable of analyzing molecular structures at the atomic level, identifying synthetic patterns that differ from the organic compounds produced by known biological systems. Some researchers focus their attention on unusual mineral formations that display characteristics inconsistent with natural formation processes. These anomalous materials, particularly those containing rare earth elements in unexpected concentrations or displaying crystal structures that don't match any known natural minerals, might represent the preserved remains of prehistoric synthetic materials that have undergone chemical transformation over geological time. The rare earth elements, those exotic materials essential to modern electronics, provide particularly intriguing possibilities for ancient material preservation. Neodymium, europium, ytterbium, and their chemical cousins play crucial roles in contemporary technology precisely because of their unique chemical properties. Advanced ancient civilizations might have discovered and utilized these same elements in their own technologies, creating material signatures that could persist across millions of years. Certain ceramics and glasses represent another category of potentially imperishable ancient materials. Modern high-tech ceramics can withstand extreme temperatures, resist chemical attack, and maintain their structural integrity under conditions that would destroy most other materials. Ancient civilizations with advanced materials, science might have developed similar ceramic technologies, creating artifacts that could survive burial in stable geological environments for millions of years. Even metal alloys, despite their general susceptibility to corrosion, might persist under specific preservation conditions. Certain exotic alloys, particularly those incorporating platinum group metals or other corrosion-resistant elements, could theoretically survive geological timescales if buried in oxygen-free environments or protected by encasing materials that prevent chemical weathering. The discovery of confirmed artificial materials in ancient rock layers would revolutionize not only archaeology, but our entire understanding of intelligence and technological development on Earth. Such findings would prove that consciousness and technology had emerged multiple times throughout our planet's history, following pathways that might differ completely from human technological evolution. The theoretical framework for recognizing ancient synthetic materials continues to evolve as materials, science advances, and archaeological analysis techniques become increasingly sophisticated. New analytical methods can detect synthetic molecular structures at increasingly subtle levels, while improved understanding of how materials change over geological time helps researchers distinguish between natural transformation processes and the signatures of artificial synthesis. Advanced spectroscopic techniques can analyze the molecular fingerprints of unusual materials, searching for synthetic patterns that indicate intelligent design rather than natural formation. Isotopic analysis can reveal whether materials form through natural processes or artificial manipulation of elements. Crystallographic studies can identify geometric structures that suggest technological rather than biological origins. Despite these advancing capabilities, no confirmed artificial materials from prehistoric civilizations have yet been identified in the archaeological record. This absence might reflect the true rarity of ancient advanced civilizations, the effectiveness of geological recycling processes in destroying even durable materials, or simply the limitations of current analytical techniques in recognizing synthetic signatures that differ from modern technological patterns. The ongoing search for ancient synthetic materials represents one of the most intriguing frontiers in archaeological science, where chemistry meets deep time in the quest to understand whether human technology represents the first flowering of advanced materials science on Earth, or merely the latest chapter in a story of technological development that spans millions of years. The plastic bottles and synthetic materials surrounding us in daily life serve as inadvertent experiments in long-term preservation, demonstrating that certain technological products can achieve a form of immortality that their creators never intended. This accidental eternity of modern materials provides both a sobering reminder of our technological impact and a tantalizing glimpse of how ancient advanced civilizations might have left their own imperishable signatures in the patient geological archives that surround us. In the deepest trenches of Earth's oceans, where sunlight has never penetrated and pressure could crush mountains, lies the most complete library of our planet's history, a vast archive where the traces of ancient advanced civilizations might rest in perfect preservation, waiting in the cold darkness for discovery by explorers brave enough to venture into the abyss. The ocean floor represents Earth's most faithful historian, recording events with patience that spans hundreds of millions of years. In certain locations, sediment layers have accumulated steadily like pages in an enormous book, each layer preserving microscopic details of climate changes, extinction events, and biological innovations that occurred when the world above bore faces we can barely imagine. This marine archive operates without interruption, collecting and preserving information about Earth's past with methodical precision that exceeds any human record-keeping system. Deep-sea drilling projects have recovered sediment cores that reveal vast periods of geological time compressed into cylinders of mud and rock. These cores contain stories written in microscopic fossils, chemical signatures, and mineral deposits that span from the present day back to epochs when continents held completely different configurations. Within layers representing millions of years of accumulated history, scientists read tales of ancient climates, massive volcanic eruptions, asteroid impacts, and the rise and fall of countless species. Within these marine sediments, researchers occasionally encounter something that doesn't belong: unusual objects that challenge conventional explanations, anomalous mineral concentrations that suggest artificial rather than natural origins, and structures that display geometric patterns inconsistent with known biological or geological processes. These discoveries emerge from the deep-like messages from forgotten worlds, carrying questions that challenge our understanding of what might have existed in Earth's ancient oceans. The deep ocean environment provides almost perfect conditions for preserving artifacts from ancient civilizations across geological timescales. The perpetual cold of abyssal depths slows chemical reactions that would otherwise break down complex materials. Crushing pressure creates stable conditions where materials remain unchanged for millions of years. The absence of oxygen prevents the biological decay processes that destroy organic materials in surface environments, while the lack of light eliminates photochemical breakdown that affects materials exposed to solar radiation. These preservation conditions mean that objects dropped into deep ocean basins millions of years ago might remain in nearly pristine condition, protected by layers of accumulated sediment from the destructive forces that erase evidence of ancient civilizations on land. Materials that would corrode, rot, or dissolve in surface environments could persist indefinitely in the stable chemistry of deep marine sediments. Advanced sonar mapping systems continue to reveal unexpected features on the ocean floor that challenge conventional understanding of marine geology. These sophisticated instruments send sound waves into the depths, creating detailed three-dimensional maps of underwater topography that reveal geometric patterns, artificial-looking structures, and deposits of materials that don't match the surrounding geological formations. Some of these discoveries display characteristics that seem almost impossible to explain through natural processes. Perfectly straight lines extending for kilometers across abyssal plains, geometric shapes that appear too regular to result from random geological forces, and structural features that suggest design rather than natural formation. These anomalies exist at depths where conventional archaeology suggests no human activity could have occurred, in locations that have remained stable for millions of years. Deep-sea submersibles equipped with high-resolution cameras and sampling equipment have captured images of underwater features that spark intense scientific debate. Stepped formations that resemble terraced architecture, angular structures that appear artificially constructed, and material compositions that differ significantly from surrounding seafloor geology. While most researchers favor natural explanations for these features, some characteristics remain difficult to account for through known geological or biological processes. The vastness of Earth's oceans means that most of the seafloor remains unexplored and unmapped. Less than 20% of the ocean floor has been surveyed with sufficient resolution to identify unusual features, leaving enormous areas where evidence of ancient civilizations could exist without detection. The deepest ocean trenches, most remote abyssal plains, and vast stretches of mid-ocean ridges remain largely mysterious, their secrets protected by crushing depths and the immense technical challenges of deep-sea exploration. Recent technological advances in underwater exploration continue to reveal new mysteries in marine environments. Autonomous underwater vehicles can now reach previously inaccessible depths, while improved sonar and imaging systems provide unprecedented detail about seafloor features. These technological capabilities occasionally uncover anomalous structures, unusual material compositions, or geometric patterns that don't match known natural processes. The ocean floor's role as Earth's memory bank suggests that if ancient advanced civilizations did exist, their most durable traces would likely be preserved in marine sediments rather than on continually changing continental surfaces. While land undergoes constant transformation through erosion, tectonic activity, and biological processes, the deep ocean provides stable environments where materials can remain undisturbed for millions of years. This preservation potential means that evidence of prehistoric technological societies might exist in forms completely unlike terrestrial archaeological sites. Ancient underwater installations, technological debris preserved in sediment layers, or artificial materials buried beneath millions of years of accumulated marine deposits could await discovery in the vast unexplored regions of Earth's ocean basins. The search for such evidence requires technological capabilities that push the boundaries of underwater exploration. Future deep-sea missions equipped with advanced analytical instruments, improved sampling systems, and artificial intelligence for pattern recognition might uncover marine archaeological sites that revolutionize understanding of intelligence and civilization on Earth. The mysteries hidden beneath Earth's oceans represent one of the greatest frontiers for archaeological discovery, where the patient preservation of marine environments might have safeguarded evidence of ancient advanced civilizations that achieved technological mastery along pathways completely different from human development. In the cold darkness of the deep sea, surrounded by crushing pressure and eternal silence, the traces of forgotten worlds might wait for explorers capable of reading the stories written in sediments that have preserved Earth's deepest secrets across the vast expanses of geological time. Hidden within ancient rocks lie atomic fingerprints, so persistent they could preserve evidence of nuclear technology for millions of years, radioactive signatures that might serve as the most durable monuments ever created by advanced civilizations, written in the universal language of atomic physics that transcends culture, biology, and even time itself. These nuclear signatures represent perhaps the most permanent traces that any technological civilization could leave behind. While organic materials decompose and metals corrode away to nothing, radioactive isotopes follow the inexorable mathematics of nuclear decay, creating atomic clocks that tick away according to the fundamental laws of physics. These isotopic patterns remain detectable across geological timescales, preserving information about nuclear processes in forms that survive long after every other trace of civilization has vanished. Nuclear technology produces distinctive radioactive elements with specific half-lives that create isotopic fingerprints unlike anything produced by natural processes. When human civilization splits uranium atoms in nuclear reactors, we create artificial elements like plutonium-239 and technetium-99 that exist nowhere in nature's repertoire. These synthetic isotopes carry permanent signatures of technological activity, creating atomic monuments that will persist for millions of years as testament to our nuclear age. The persistence of these nuclear signatures emerges from the fundamental nature of radioactive decay, which operates according to mathematical laws that remain constant across cosmic time. A plutonium-239 atom created in a nuclear reactor today will have a half-life of 24,100 years, regardless of temperature, pressure, or chemical environment. This radioactive signature will remain detectable for hundreds of thousands of years, creating a permanent marker of technological nuclear activity in the geological record. Natural uranium deposits occasionally reveal isotopic ratios that tell extraordinary stories about prehistoric nuclear reactions. The Oklo natural reactor in Gabon represents the most famous example, where geological conditions 2 billion years ago created sustained nuclear fission reactions that operated for hundreds of thousands of years. These natural reactors left distinctive isotopic signatures that remain clearly detectable today, demonstrating how nuclear processes can create permanent records in the geological archive. However, some researchers have identified other radioactive anomalies in ancient rocks that don't match the expected patterns from known natural processes. These mysterious isotopic signatures suggest nuclear reactions that operated under conditions different from the Oklo phenomenon, raising questions about whether some unusual radioactive patterns might indicate artificial rather than natural nuclear processes. The production of synthetic elements through advanced nuclear technologies would create isotopic patterns that no natural process could duplicate. Elements like technetium, which has no stable isotopes and decays relatively quickly, exist nowhere in nature, but appear commonly in nuclear waste from human reactors. The discovery of technetium isotopes in ancient geological formations would provide almost incontrovertible evidence of prehistoric nuclear technology. Similarly, plutonium isotopes in specific ratios, characteristic of nuclear reactors, would represent signatures that could only result from deliberate nuclear engineering, while uranium can undergo natural nuclear reactions under extraordinary geological conditions. Plutonium production requires controlled nuclear processes that concentrate and purify radioactive materials through techniques that nature cannot duplicate without intelligent intervention. Advanced nuclear technologies might have produced even more exotic isotopic patterns that persist long after the civilizations that created them disappeared into deep time. Hypothetical prehistoric societies might have developed fusion reactors, exotic nuclear processes, or transmutation technologies that created radioactive signatures unlike anything in our current nuclear experience. The search for ancient nuclear signatures requires sophisticated radiochemical analysis that pushes the boundaries of isotopic measurement. Scientists must distinguish between natural radioactive decay patterns and potential artificial sources, while accounting for the effects of geological processes that can modify isotopic ratios over millions of years. This detective work demands extraordinary analytical precision and comprehensive understanding of how radioactive elements behave in different geological environments. Natural processes can create radioactive anomalies through various mechanisms that researchers must carefully consider. Cosmic ray bombardment can produce unusual isotopes in surface rocks, while certain geological conditions can concentrate naturally occurring radioactive elements in patterns that might superficially resemble artificial nuclear signatures. Distinguishing between these natural processes and potential technological sources requires detailed analysis of isotopic ratios, geological context, and the physical mechanisms that could produce observed radioactive patterns. Despite these analytical challenges, certain isotopic signatures would be virtually impossible to explain through natural processes alone. The simultaneous presence of multiple synthetic isotopes in specific ratios, the occurrence of short-lived radioactive elements that should have decayed away millions of years ago, or isotopic patterns that match the characteristic signatures of controlled nuclear reactions would provide compelling evidence for prehistoric nuclear technology. The theoretical framework for recognizing ancient nuclear signatures continues to evolve as radiochemical analysis techniques become more sophisticated and our understanding of natural radioactive processes becomes more complete. Advanced mass spectrometry can detect individual atoms of rare isotopes, while improved geological dating methods help distinguish between recent contamination and genuinely ancient radioactive signatures. Some of the most intriguing possibilities involve nuclear signatures that might indicate energy sources or industrial processes completely unlike modern nuclear technology. Ancient civilizations might have developed biological nuclear processes, quantum nuclear engineering, or exotic nuclear reactions that created isotopic fingerprints unlike anything in contemporary nuclear science. While natural explanations exist for most radioactive anomalies discovered in the geological record, the theoretical possibility remains that some unusual isotopic patterns might preserve evidence of nuclear technologies developed by prehistoric civilizations that achieved atomic mastery along pathways different from human nuclear development. The search for these ancient nuclear signatures represents one of the most scientifically rigorous approaches to detecting prehistoric advanced civilizations, using the permanent language of atomic physics to search for technological signatures that could survive across millions of years of geological time. In the patient decay of radioactive atoms, the achievements of forgotten nuclear civilizations might continue to tick away like atomic clocks, marking time according to the fundamental constants that govern the universe itself. Within the perfect atomic lattices of crystals lies a storage medium so durable it could preserve the complete knowledge of an advanced civilization for billions of years. Natural libraries written in the language of atomic arrangement, where information encoded in crystal structures might wait with geological patience for minds sophisticated enough to decode their mineral memories. Crystals represent nature's most persistent information storage systems, possessing remarkable properties that allow them to maintain atomic-level patterns across timescales that dwarf human comprehension. Unlike organic materials that decompose or metals that corrode, crystalline structures resist erosion, weathering, and tectonic forces through molecular bonds that remain stable under the temperature and pressure conditions found throughout Earth's geological environments. Quartz crystals demonstrate this extraordinary durability, maintaining their precise atomic arrangements for billions of years while preserving microscopic details of their formation conditions. The hexagonal symmetry of quartz reflects perfect mathematical relationships, encoded in silicon and oxygen atoms that arrange themselves according to fundamental physical laws. These crystalline patterns serve as natural archives that record information about temperature, pressure, and chemical conditions during their formation. Diamonds represent even more remarkable examples of crystalline permanence, with carbon atoms locked in cubic arrangements so stable they resist virtually all forms of natural alteration. The diamond crystal structure preserves information about deep mantle conditions existing billions of years ago, carrying within their atomic lattices records of pressures, temperatures, and chemical compositions from Earth's interior. These gemstones serve as time capsules that transport information from the planet's deep past to the present day. Advanced civilizations might have recognized these crystalline storage properties and developed technologies for encoding information directly into mineral structures. Hypothetical prehistoric societies could have created artificial crystal formations designed specifically for long-term information preservation, embedding knowledge into atomic arrangements that would survive geological timescales while remaining readable to future civilizations with appropriate decoding technologies. The potential for crystalline information storage emerges from the precise control that intelligent beings might achieve over crystal growth conditions. By manipulating temperature, pressure, chemical composition, and electromagnetic fields during crystal formation, advanced civilizations could theoretically encode complex information patterns into the three-dimensional atomic structures of growing minerals. Some researchers study unusual crystal formations that display geometric patterns or structural anomalies inconsistent with known natural formation processes. These crystalline anomalies appear in locations where geological conditions should produce different mineral structures, or display symmetries and arrangements that seem too precise to result from random natural processes operating without intelligent guidance. Certain quartz formations display internal structures that appear almost artificially organized. Parallel planes of inclusions, geometric void patterns, or regular arrangements of trace elements that create optical effects resembling technological rather than natural origins. While most geologists favor explanations involving specific formation conditions or unusual chemical environments, some structural patterns remain difficult to account for through known natural processes. Advanced crystalline technologies might have included information encoding systems that stored data in multiple dimensions simultaneously. Three-dimensional crystal structures could theoretically contain vastly more information than two-dimensional storage media, with atomic arrangements encoding complex knowledge in forms that combine digital precision with geological permanence. The search for artificial crystal structures requires sophisticated analytical techniques that probe mineral properties at the atomic level. Electron microscopy can reveal internal structures invisible to conventional optical examination, while X-ray crystallography analyzes the precise arrangement of atoms within crystal lattices. Atomic force microscopy provides surface detail at scales measured in individual atomic diameters. These analytical tools occasionally reveal crystalline properties that challenge conventional understanding of natural mineral formation. Certain crystals display unusual optical characteristics, light polarization effects, refractive indices, or spectroscopic signatures that don't match the expected properties of their mineral compositions. Others show anomalous electrical conductivity patterns or electromagnetic behaviors that suggest structural modifications beyond typical natural variation. Specific examples of crystalline anomalies include quartz formations with internal structures that appear too regular to result from natural growth processes, diamonds containing trace elements in patterns that don't match known natural diamond formation conditions, and mineral specimens displaying optical properties that require atomic arrangements not typically produced by geological processes. The theoretical framework for recognizing artificial crystalline structures continues to evolve as analytical techniques become more sophisticated and our understanding of natural crystal formation becomes more complete. Advanced spectroscopic methods can detect subtle variations in atomic arrangements, while improved understanding of crystal growth processes helps distinguish between natural formation mechanisms and potential technological manipulation. Some researchers explore whether ancient crystalline technologies might have operated according to principles completely different from modern information storage systems. Rather than encoding digital information, prehistoric civilizations might have developed crystalline consciousness interfaces, mineral-based computing systems, or quantum information storage methods that utilize properties of crystal structures we haven't yet discovered. The possibility of biological crystalline technologies adds another dimension to the search for ancient mineral artifacts. Some organisms can produce crystalline structures with extraordinary precision. The magnetic crystals in bacterial navigation systems, the crystalline teeth of certain mollusks, or the sophisticated optical crystals in some deep-sea creatures. Advanced ancient civilizations might have developed biotechnologies that grew crystalline information storage systems using controlled biological processes. While most unusual crystal formations have natural explanations involving specific geological conditions, rare chemical environments, or unique formation histories, the theoretical possibility remains that some mineral structures might preserve technological achievements from prehistoric advanced civilizations. The discovery of confirmed artificial crystalline structures would revolutionize understanding of both ancient intelligence and the potential applications of crystalline technology. The search for crystalline memories represents one of the most intriguing intersections between geology, materials science, and archaeology, where the patient persistence of mineral structures might preserve information from advanced civilizations that achieve technological mastery over atomic arrangements. In the perfect symmetries and precise atomic patterns of Earth's crystalline treasures, the knowledge of forgotten worlds might wait like geological libraries, their mineral pages filled with information encoded in the universal language of crystal structure. These crystalline archives could contain not just records of ancient technological achievements, but complete databases of prehistoric knowledge, scientific discoveries, cultural information, or even consciousness patterns, preserved in atomic arrangements so stable they could outlast the mountain ranges that contain them, waiting for future minds capable of reading the memories locked within crystal lattices across the vast expanses of geological time. Within the perfect atomic lattices of crystals lies a storage medium so durable it could preserve the complete knowledge of an advanced civilization for billions of years. Natural libraries written in the language of atomic arrangement, where information encoded in crystal structures might wait with geological patience for minds sophisticated enough to decode their mineral memories. Crystals represent nature's most persistent information storage systems, possessing remarkable properties that allow them to maintain atomic-level patterns across timescales that dwarf human comprehension. Unlike organic materials that decompose or metals that corrode, crystalline structures resist erosion, weathering, and tectonic forces through molecular bonds that remain stable under the temperature and pressure conditions found throughout Earth's geological environments. Quartz crystals demonstrate this extraordinary durability, maintaining their precise atomic arrangements for billions of years, while preserving microscopic details of their formation conditions. The hexagonal symmetry of quartz reflects perfect mathematical relationships encoded in silicon and oxygen atoms that arrange themselves according to fundamental physical laws. These crystalline patterns serve as natural archives that record information about temperature, pressure, and chemical conditions during their formation. Diamonds represent even more remarkable examples of crystalline permanence, with carbon atoms locked in cubic arrangements so stable they resist virtually all forms of natural alteration. The diamond crystal structure preserves information about deep mantle conditions existing billions of years ago, carrying within their atomic lattices records of pressures, temperatures, and chemical compositions from Earth's interior. These gemstones serve as time capsules that transport information from the planet's deep past to the present day. Advanced civilizations might have recognized these crystalline storage properties and developed technologies for encoding information directly into mineral structures. Hypothetical prehistoric societies could have created artificial crystal formations designed specifically for long-term information preservation, embedding knowledge into atomic arrangements that would survive geological timescales while remaining readable to future civilizations with appropriate decoding technologies. The potential for crystalline information storage emerges from the precise control that intelligent beings might achieve over crystal growth conditions. By manipulating temperature, pressure, chemical, composition, and electromagnetic fields during crystal formation, advanced civilizations could theoretically encode complex information patterns into the three-dimensional atomic structures of growing minerals. Some researchers study unusual crystal formations that display geometric patterns or structural anomalies inconsistent with known natural formation processes. These crystalline anomalies appear in locations where geological conditions should produce different mineral structures, or display symmetries and arrangements that seem too precise to result from random natural processes operating without intelligent guidance. Certain quartz formations display internal structures that appear almost artificially organized, parallel planes of inclusions, geometric void patterns, or regular arrangements of trace elements that create optical effects resembling technological rather than natural origins. While most geologists favor explanations involving specific formation conditions or unusual chemical environments, some structural patterns remain difficult to account for through known natural processes. Advanced crystalline technologies might have included information encoding systems that stored data in multiple dimensions simultaneously. Three-dimensional crystal structures could theoretically contain vastly more information than two-dimensional storage media, with atomic arrangements encoding complex knowledge in forms that combine digital precision with geological permanence. The search for artificial crystal structures requires sophisticated analytical techniques that probe mineral properties at the atomic level. Electron microscopy can reveal internal structures invisible to conventional optical examination, while X-ray crystallography analyzes the precise arrangement of atoms within crystal lattices. Atomic force microscopy provides surface detail at scales measured in individual atomic diameters. These analytical tools occasionally reveal crystalline properties that challenge conventional understanding of natural mineral formation. Certain crystals display unusual optical characteristics, light polarization effects, refractive indices, or spectroscopic signatures that don't match the expected properties of their mineral compositions. Others show anomalous electrical conductivity patterns or electromagnetic behaviors that suggest structural modifications beyond typical natural variation. Specific examples of crystalline anomalies include quartz formations with internal structures that appear too regular to result from natural growth processes, diamonds containing trace elements in patterns that don't match known natural diamond formation conditions, and mineral specimens displaying optical properties that require atomic arrangements not typically produced by geological processes. The theoretical framework for recognizing artificial crystalline structures continues to evolve as analytical techniques become more sophisticated and our understanding of natural crystal formation becomes more complete. Advanced spectroscopic methods can detect subtle variations in atomic arrangements, while improved understanding of crystal growth processes helps distinguish between natural formation mechanisms and potential technological manipulation. Some researchers explore whether ancient crystalline technologies might have operated according to principles completely different from modern information storage systems, Rather than encoding digital information, prehistoric civilizations might have developed crystalline consciousness interfaces, mineral-based computing systems, or quantum information storage methods that utilize properties of crystal structures we haven't yet discovered. The possibility of biological crystalline technologies adds another dimension to the search for ancient mineral artifacts. Some organisms can produce crystalline structures with extraordinary precision, the magnetic crystals in bacterial navigation systems, the crystalline teeth of certain mollusks, or the sophisticated optical crystals in some deep-sea creatures. Advanced ancient civilizations might have developed biotechnologies that grew crystalline information storage systems using controlled biological processes. While most unusual crystal formations have natural explanations involving specific geological conditions, rare chemical environments, or unique formation histories, the theoretical possibility remains that some mineral structures might preserve technological achievements from prehistoric advanced civilizations. The discovery of confirmed artificial crystalline structures would revolutionize understanding of both ancient intelligence and the potential applications of crystalline technology. The search for crystalline memories represents one of the most intriguing intersections between geology, materials science, and archaeology, where the patient persistence of mineral structures might preserve information from advanced civilizations that achieved technological mastery over atomic arrangements. In the perfect symmetries and precise atomic patterns of Earth's crystalline treasures, the knowledge of forgotten worlds might wait like geological libraries, their mineral pages filled with information encoded in the universal language of crystal structure. These crystalline archives could contain not just records of ancient technological achievements, but complete databases of prehistoric knowledge, scientific discoveries, cultural information, or even consciousness patterns, preserved in atomic arrangements so stable they could outlast the mountain ranges that contain them, waiting for future minds capable of reading the memories locked within crystal lattices across the vast expanses of geological time. The greatest irony of metallurgy may be that while metals enabled the rise of technological civilizations, they also ensure those civilizations leave almost no metallic trace of their achievements, corroding away across geological time in a process so thorough that even the most sophisticated ancient alloys would dissolve back into the elements from which they came, leaving only chemical whispers in the rock record. This metallurgical paradox reveals both the promise and the futility of searching for prehistoric technological societies through their metallic achievements. Metals provided the foundation for human industrial civilization, enabling everything from simple tools to complex machinery. Yet these same materials follow chemical laws that make them some of the least durable artifacts any civilization could create when viewed across geological timescales. Advanced metallurgy produces distinctive signatures that differ dramatically from natural metal deposits found in ore bodies. When civilizations smelt metals from raw ores, they create purified materials with isotopic ratios, alloy compositions, and trace element patterns that nature rarely duplicates through geological processes alone. These metallurgical fingerprints could theoretically serve as permanent markers of technological activity, preserving evidence of industrial sophistication in the chemical signatures of processed metals. The isotopic manipulation involved in advanced metallurgy creates particularly distinctive signatures. When metals are refined, alloyed, and reprocessed through multiple industrial steps, they acquire isotopic ratios that reflect artificial rather than natural processes. The precise control over metal composition achieved by advanced metallurgy produces chemical fingerprints that could remain detectable even after the original metallic artifacts have completely dissolved away. However, the preservation of metallic artifacts across geological time faces nearly insurmountable chemical obstacles. Most metals exist in thermodynamically unstable states when exposed to oxygen, water, and other reactive compounds abundant in Earth's surface environment. The same chemical reactivity that makes metals useful for technological applications also ensures their inevitable return to more stable oxidized forms through corrosion processes that operate with geological patience. Iron, the backbone of industrial civilization, exemplifies this metallurgical mortality, Even the finest steel alloys succumb to oxidation processes that convert metallic iron back into rust, iron oxide, that disperses through soil and water systems as microscopic particles. The iron atoms that once formed sophisticated machinery eventually migrate through countless chemical transformations, becoming incorporated into new mineral formations that bear no resemblance to their technological origins. Copper faces similar chemical destiny, weathering into green copper carbonate compounds that gradually dissolve and migrate through groundwater systems. The bronze artifacts that represent humanity's earliest metallurgical achievements survive only under extraordinary preservation conditions, rapid burial in oxygen-free environments, chemical stabilization through specific soil conditions, or protection within sealed chambers that exclude corrosive agents. Even modern high-tech alloys designed for maximum durability would eventually succumb to chemical processes operating across millions of years. Stainless steel, titanium alloys, and exotic superalloys represent temporary victories against corrosion, but geological time operates on scales that make even these metallurgical achievements ephemeral when measured against the persistence of rock formations and crystal structures. The search for ancient metallurgical signatures therefore focuses not on surviving metallic artifacts, but on the chemical traces that advanced metal processing might have left in the geological record. Unusual concentrations of specific metals in sedimentary layers could indicate locations where ancient smelting operations once concentrated ores and produced refined metals. These metallurgical sites might preserve chemical fingerprints of technological activity long after every physical artifact had dissolved away. Anomalous isotopic ratios in metal-bearing rock formations provide another potential pathway for detecting prehistoric metallurgy. Natural ore deposits typically display isotopic signatures that reflect the geological processes involved in their formation. Artificial metal processing could create isotopic patterns that differ from these natural signatures, potentially preserving evidence of technological manipulation in the chemical composition of ancient sediments. Rare earth element patterns offer particularly promising possibilities for detecting ancient metallurgical activity. These exotic metals play crucial roles in modern high-technology applications precisely because of their unique chemical properties. Advanced ancient civilizations might have discovered and utilized these same elements in their own technologies, creating rare earth element concentrations and patterns that persist in the geological record as evidence of sophisticated metallurgical knowledge. Some researchers examine ancient metal deposits for evidence of purification techniques that would indicate technological rather than natural concentration processes. Natural metal deposits often contain complex mixtures of different metals and mineral phases. Artificial metallurgical processing typically produces much purer metal concentrations with specific alloy compositions that reflect deliberate technological choices rather than random geological mixing. Certain precious metals and platinum group elements provide the best opportunities for preserving direct evidence of prehistoric metallurgical activity. Gold, platinum, and related metals resist corrosion under most environmental conditions, potentially surviving as recognizable metallic particles even after millions of years of burial. These noble metals could theoretically preserve evidence of ancient technological processing in the form of artificial alloys, refined compositions, or concentrated deposits that indicate technological rather than natural origins. The absence of obvious ancient metallic artifacts in the archaeological record doesn't necessarily preclude the existence of prehistoric advanced civilizations. Instead, this metallurgical silence reflects the fundamental chemical instability of most metals when exposed to geological processes operating across deep time. The efficiency of natural recycling systems ensures that technological metals return to their constituent elements through chemical pathways that erase evidence of their artificial origins. This metallurgical recycling operates through mechanisms so thorough they leave virtually no trace of even the most sophisticated metallic technologies. The iron atoms that once formed the structural framework of hypothetical ancient cities now exist as rust particles dispersed through soils. The copper that once carried electrical currents has become carbonate minerals in distant rock formations, and the complex alloys that once enabled advanced technologies have dissolved back into the elemental components from which they originally came. The silence of metals across geological time thus represents one of the most significant challenges facing the search for prehistoric advanced civilizations. While metallurgy enabled the rise of technological societies, the chemical properties of metals ensure that these achievements leave only the faintest chemical traces in the geological record. The discovery of ancient metallurgical signatures would require sophisticated geochemical analysis, capable of detecting technological fingerprints preserved in forms that bear no obvious resemblance to their original metallic sources. Yet this very silence might itself carry information about the sophistication of ancient metallurgical knowledge. Civilizations that understood the chemical instability of metals across geological time might have deliberately chosen more durable materials for their most important technological achievements, leaving behind crystalline, ceramic, or synthetic polymer artifacts designed specifically to outlast the metallic tools that created them. What if the greatest masterpieces of ancient advanced civilizations were not built from stone or metal, but woven into the very fabric of life itself, genetic masterworks that continue to function in every living cell? Biological technologies so sophisticated they became indistinguishable from evolution, carrying the achievements of forgotten civilizations forward through millions of years of reproduction and adaptation. This possibility emerges from recognizing that advanced civilizations might have preferred biological engineering over mechanical technology, creating living systems that self-repair, reproduce, and evolve, rather than building artifacts that would inevitably corrode and decay across geological time. Such biological interventions could have left permanent traces in the evolutionary record through genetic manipulations, directed breeding programs, or biological engineering projects that created lasting changes in Earth's biosphere. The history of life on Earth contains several evolutionary events so dramatic and rapid they challenge conventional understanding of how biological complexity develops through natural selection. The Cambrian explosion, occurring roughly 540 million years ago, saw the sudden appearance of virtually all major animal body plans within a geological instant. Complex organisms with sophisticated sensory systems, elaborate feeding mechanisms, and intricate body structures appearing in the fossil record without obvious evolutionary precursors. This biological revolution introduced innovations that seem almost impossibly sophisticated for their time: compound eyes capable of detecting polarized light, complex nervous systems processing multiple sensory inputs, and biomechanical structures displaying engineering principles that modern technology has only recently begun to understand. The speed and sophistication of these developments have prompted some researchers to question whether natural evolutionary processes alone could account for such rapid biological innovation. The rapid diversification of flowering plants presents another evolutionary puzzle that defies easy explanation through conventional natural selection. Angiosperms appeared suddenly in the fossil record and quickly diversified into the complex pollination systems, biochemical pathways, and reproductive strategies that dominate modern terrestrial ecosystems. Charles Darwin himself called the origin of flowering plants an abominable mystery, recognizing that their sudden appearance challenged the gradual evolutionary change his theory predicted. The emergence of complex neural systems capable of consciousness, memory, and abstract reasoning represents perhaps the most extraordinary development in biological history. The transition from simple nerve networks to sophisticated brains capable of processing information, storing memories, and generating conscious experience occurred with remarkable speed in evolutionary terms, producing cognitive capabilities that seem disproportionate to their apparent survival advantages. Genetic analysis of modern organisms occasionally reveals molecular structures and capabilities that appear to have emerged too rapidly through random mutation and natural selection alone. Certain genetic sequences display optimization that suggests deliberate engineering rather than gradual evolutionary refinement. Complex biochemical pathways involving dozens of precisely coordinated enzymes sometimes appear fully formed in the genetic record without evidence of the intermediate steps that natural evolution should produce. Advanced civilizations capable of genetic manipulation might have developed biological technologies that operated through principles completely different from modern genetic engineering. Rather than crude insertion of foreign genes, prehistoric biotechnology might have achieved precise control over evolutionary processes, guiding biological development through techniques that accelerated beneficial mutations while suppressing harmful changes. Such biological intervention might have taken forms that remain nearly invisible to contemporary analysis. Ancient genetic engineers might have developed sophisticated biological programming languages encoded in DNA sequences that appear natural to modern eyes. They could have created self-modifying genetic systems that continue to evolve according to predetermined parameters long after their creators disappeared. The search for biological signatures of prehistoric intervention requires sophisticated molecular analysis that pushes the boundaries of comparative genomics and evolutionary modeling. Researchers must distinguish between the signatures of natural evolutionary processes and potential artificial influences that might have guided biological development along specific pathways. Certain biological structures display characteristics that suggest engineering optimization rather than evolutionary accident. The bacterial flagellum operates as a sophisticated rotary motor, with components that function like engineered bearings, drive shafts, and propeller systems. This molecular machine displays irreducible complexity. Remove any component and the entire system fails to function, suggesting that it might have been designed as an integrated system rather than assembled gradually through natural selection. The vertebrate eye demonstrates optical precision that rivals sophisticated camera systems with corneas, lenses, and retinal structures that work together to focus light with extraordinary accuracy. The biochemistry of vision involves cascades of precisely coordinated molecular reactions that convert light energy into electrical signals with efficiency that exceeds most artificial photosensitive systems. Photosynthesis represents perhaps the most sophisticated biological technology on Earth, converting solar energy into chemical energy through quantum mechanical processes so complex they require advanced physics to understand. The molecular machinery of photosynthesis operates at nearly 100% efficiency in converting absorbed photons into chemical energy, displaying optimization that suggests careful engineering rather than random evolutionary development. These biological systems raise profound questions about the boundaries between natural evolutionary innovation and potential technological intervention. While evolutionary biologists have developed explanations for how complex systems can arise through natural selection, the speed and sophistication of some biological innovations challenge conventional understanding of evolutionary timescales and mechanisms. Advanced ancient civilizations might have developed biotechnologies that worked with evolutionary processes rather than against them, creating genetic modifications that enhanced natural selection rather than replacing it. Such biological technologies might have accelerated evolution along beneficial pathways while maintaining the appearance of natural development. The theoretical framework for recognizing biological intervention continues to evolve as genomic analysis techniques become more sophisticated and our understanding of natural evolutionary processes becomes more complete. Advanced computational methods can now model evolutionary pathways with unprecedented precision, helping distinguish between natural evolutionary innovations and potential signatures of biological engineering. Some researchers explore whether certain biological systems might contain embedded information or technological capabilities that served functions beyond simple survival advantages. Complex genetic regulatory networks, sophisticated cellular signaling systems, or biochemical pathways with apparent redundancy might represent biological technologies whose original purposes have been obscured by millions of years of evolutionary modification. The possibility that advanced civilizations left their greatest achievements encoded in the genetics of living organisms suggests that every creature on Earth might carry within its cells the technological legacy of prehistoric biotechnological civilizations. These biological interventions would represent the ultimate form of technological persistence, living systems that continue to function, reproduce, and evolve, while preserving the essential innovations that enabled their creation. In this view, the remarkable diversity and sophistication of life on Earth might reflect not just the creative power of natural evolution, but the accumulated achievements of multiple biological civilizations that chose to embed their technological mastery in self-perpetuating living systems, rather than creating artifacts that would inevitably decay across geological time. Beneath our feet lies a hidden world more vast than all the cities on Earth's surface, an intricate network of caves, tunnels, and underground chambers where ancient civilizations might have built entire subterranean empires that continue to exist in perfect darkness, their architectural achievements protected by kilometers of rock from the surface catastrophes that erased their above-ground counterparts. This underground frontier represents one of the most promising environments for discovering traces of prehistoric advanced civilizations. While surface structures succumb to erosion, weathering, and tectonic forces across geological time, subterranean spaces provide natural sanctuaries where artificial constructions could survive for millions of years in stable conditions that preserve even the most delicate architectural details. The scale of Earth's underground realm staggers human comprehension. Vast cave systems extend for hundreds of kilometers. Through limestone formations, lava tubes stretch beneath entire mountain ranges, and interconnected cavern networks create three-dimensional mazes that dwarf any human construction project. Within this subterranean landscape, advanced civilizations could have built underground cities, transportation networks, and industrial complexes that remain completely hidden from surface observation. Archaeological evidence demonstrates that sophisticated underground construction has been within human capabilities for millennia, suggesting that more advanced prehistoric civilizations might have achieved even greater subterranean engineering feats. The underground cities of Cappadocia in Turkey extend through multiple levels carved directly from volcanic rock, accommodating thousands of inhabitants with elaborate ventilation systems, storage chambers, and defensive structures that remain functional today. European cities conceal extensive tunnel networks that span centuries of construction, from Roman-era aqueducts and medieval escape routes to more recent military installations. These underground systems demonstrate how civilizations consistently turn to subterranean construction for protection, storage, and specialized activities that require isolation from surface conditions. Mysterious chambers discovered beneath ancient monuments around the world reveal that underground construction often accompanied major surface building projects. The Great Pyramid contains internal chambers and passages that suggest sophisticated understanding of subterranean architecture, while similar hidden chambers beneath temples, monuments, and ceremonial sites indicate that ancient civilizations regularly incorporated underground elements into their most important constructions. Advanced civilizations operating millions of years ago might have preferred underground construction as their primary architectural approach, creating subterranean cities that would naturally survive the surface catastrophes, climate changes, and geological transformations that occurred throughout Earth's history. These underground civilizations might have developed entirely different approaches to urban planning, agriculture, and industrial production, optimized for subterranean environments. The search for prehistoric underground networks requires sophisticated detection technologies that can identify artificial structures distinguishable from natural cave systems. Ground-penetrating radar sends electromagnetic pulses deep into the Earth, creating detailed maps of subsurface features that reveal geometric patterns, regular structures, and void spaces that might indicate artificial rather than natural origin. Seismic tomography uses sound waves to create three-dimensional images of underground structures, revealing density variations and structural patterns that help distinguish between natural rock formations and potential artificial constructions. Advanced cave mapping techniques employing laser, scanning, and digital modeling can detect subtle architectural features that suggest intelligent design rather than random geological processes. These detection methods occasionally reveal underground anomalies that challenge conventional explanations. Perfectly geometric patterns in tunnel networks suggest deliberate planning rather than natural water erosion. Chambers with acoustic properties that enhance sound transmission or create specific resonance effects might indicate intentional acoustic engineering. Caverns containing unusual mineral deposits or structural features that don't match surrounding geology could represent remnants of ancient technological activities. The deep underground environment provides almost perfect preservation conditions for ancient constructions. Stable temperatures protect materials from thermal expansion and contraction that causes surface structures to crack and deteriorate. The absence of oxygen prevents biological decay processes that destroy organic materials, while isolation from surface water systems eliminates the chemical weathering that dissolves even durable construction materials. These preservation advantages mean that underground structures built millions of years ago might remain in nearly pristine condition, protected by rock overburden from the destructive forces that erase surface evidence of ancient civilizations. Artifacts, architectural details, and even organic materials could survive indefinitely in deep underground environments that maintain stable chemical and physical conditions across geological timescales. Some underground explorations have revealed chambers and passages that display characteristics difficult to explain through known natural processes. Regular geometric shapes carved into solid rock, precisely engineered ventilation systems that continue to function after millennia, and structural elements that suggest advanced understanding of load distribution and architectural stability. Certain cave systems contain features that appear almost impossibly sophisticated for their apparent age. Spiral staircases carved into living rock, chambers with perfect acoustic properties for amplifying sound, and tunnel networks that follow geometric patterns more consistent with intelligent planning than random natural formation. While most researchers favor natural explanations for these features, some characteristics remain difficult to account for through conventional geological processes. The possibility that Earth's underground realm contains architectural achievements from advanced prehistoric civilizations transforms speleology from recreational cave exploration into archaeological investigation. Every newly discovered cave system becomes a potential archaeological site, every unusual underground feature a possible technological artifact, from civilizations that mastered subterranean construction techniques beyond current human capabilities. Advanced civilizations might have developed underground transportation systems, subterranean agricultural technologies, and industrial processes specifically designed for cave environments. These underground societies could have achieved technological sophistication that rivaled or exceeded surface civilizations while remaining completely hidden from conventional archaeological investigation. The interconnected nature of many cave systems suggests that prehistoric underground civilizations might have created continent-spanning networks that connected distant regions through subterranean pathways. These underground transportation systems could have enabled trade, communication, and cultural exchange across vast distances, while avoiding the surface hazards that limited the development of early human civilizations. Future exploration of Earth's underground frontier will likely reveal increasingly sophisticated examples of ancient subterranean construction as detection technologies improve and access to deep cave systems becomes more feasible. The underground realm represents one of the most promising frontiers for discovering evidence of prehistoric advanced civilizations that chose to build their greatest achievements in the permanent darkness beneath Earth's surface. These subsurface investigations suggest that the true scope of ancient architectural achievement might remain largely hidden in underground networks that continue to exist in perfect preservation, waiting for explorers equipped with sufficiently advanced detection technologies to reveal the subterranean wonders created by civilizations that understood the advantages of building their most important constructions beyond the reach of surface catastrophes and geological change. At the deepest level of reality, where particles exist in multiple states simultaneously and information transcends the boundaries of space and time, quantum mechanics suggests a startling possibility. Every event that has ever occurred in the universe might leave permanent traces in the quantum fabric itself, creating an invisible archive where the technological achievements of ancient advanced civilizations could be preserved in the fundamental structure of atoms, fields, and the quantum vacuum. This possibility emerges from quantum archaeology, a theoretical field that explores whether information about past events might be encoded in quantum systems that persist across geological timescales. Unlike classical information that degrades and disappears over time, quantum information displays properties that could theoretically preserve records of technological activities from prehistoric civilizations in forms that transcend the limitations of physical artifacts. Quantum mechanics reveals that information, once created, cannot be destroyed according to fundamental physical laws. The quantum no-cloning theorem and information conservation principles suggest that every quantum interaction leaves permanent traces in the structure of reality itself. These quantum signatures might persist long after the physical systems that created them have disappeared, encoded in subtle modifications to atomic structures, quantum field configurations, or the probabilistic patterns that govern particle behavior. Advanced quantum technologies developed by prehistoric civilizations might have left detectable signatures in these fundamental quantum systems. Hypothetical ancient quantum computers could have created modifications to the quantum vacuum that remain accessible to sufficiently sophisticated measurement techniques. Quantum communication networks might have established entanglement patterns that persist across geological time. Exotic quantum engineering projects could have altered the basic quantum field fluctuations in ways that modern quantum sensors might eventually detect. The search for quantum archaeological evidence requires measurement techniques that operate at the theoretical limits of quantum sensitivity. Atomic interferometry can detect minute changes in atomic behavior that might indicate past quantum technological activities. Advanced quantum sensors can measure field fluctuations with precision approaching fundamental quantum limits. Quantum information analysis techniques might identify patterns in quantum noise that suggest artificial rather than natural origins. These quantum detection methods push beyond conventional physics into realms where measurement itself becomes a form of time travel, potentially accessing information about past events through the quantum correlations that connect all matter and energy across space and time. Quantum archaeological investigations operate on the principle that the universe maintains perfect records of its own history in the quantum information patterns that govern atomic behavior. Some researchers explore whether consciousness itself might leave quantum signatures that could preserve information about prehistoric intelligent beings and their technological capabilities. The quantum theories of consciousness suggest that aware minds might create distinctive patterns in quantum field configurations that persist beyond the biological systems that generated them. If consciousness operates through quantum mechanisms, as some theories propose, then the thoughts, memories, and technological knowledge of ancient civilizations might remain encoded in the quantum structures of atoms that once comprised their neural systems. These quantum consciousness signatures could theoretically be accessed through advanced quantum measurement techniques that detect the subtle quantum correlations associated with intelligent information processing. Quantum archaeological investigations examine whether artificial quantum systems from ancient civilizations might have left detectable traces in fundamental physical processes. Ancient quantum computers operating millions of years ago could have created modifications to local quantum field configurations that remain measurable today. Quantum communication networks might have established entanglement patterns between distant locations that persist as quantum correlations detectable by modern instrumentation. The theoretical framework for quantum archaeology draws from quantum information theory, which demonstrates that information encoded in quantum systems displays remarkable persistence properties. Quantum error correction mechanisms, decoherence suppression techniques, and quantum information storage methods might have allowed ancient civilizations to preserve technological information in quantum systems designed to survive across geological timescales. Advanced quantum technologies might have included quantum memory systems that stored information in atomic spin configurations, quantum field manipulation devices that modified vacuum energy patterns, or consciousness transfer technologies that preserved intelligent information in quantum structures that transcended biological limitations. The quantum vacuum itself might serve as an archaeological medium where traces of ancient technological activities remain preserved in the zero-point energy fluctuations that permeate empty space. Some theoretical models suggest that high-energy quantum processes might create permanent modifications to vacuum structure that could preserve information about the technological activities that generated them. Quantum field theory provides mathematical frameworks for understanding how information might be encoded in fundamental field configurations that persist across cosmic timescales. Virtual particle interactions, vacuum polarization effects, and quantum field fluctuations might contain encrypted records of past quantum technological activities accessible through advanced theoretical physics and experimental quantum mechanics. The development of quantum archaeology techniques requires advances in multiple areas of quantum technology. Improved quantum sensors with sensitivity approaching fundamental physical limits, quantum information processing systems capable of analyzing complex quantum correlations, and theoretical frameworks for interpreting quantum archaeological data represent essential tools for investigating prehistoric quantum technologies. Future quantum archaeological investigations might reveal that ancient advanced civilizations achieved quantum technological mastery that exceeded current human capabilities. Prehistoric quantum engineers might have developed techniques for manipulating atomic structure, controlling quantum field configurations, or preserving consciousness in quantum information patterns that remain beyond contemporary understanding. The possibility that quantum information from ancient civilizations persists in the quantum structures around us transforms every atom into a potential archaeological artifact, every quantum interaction into a possible communication from the deep past. The quantum fields that govern atomic behavior might contain libraries of prehistoric technological knowledge encoded in quantum correlations that connect modern matter to the ancient quantum systems that helped create it. Quantum archaeology suggests that the ultimate archaeological discovery might not involve digging in the ground or analyzing chemical signatures, but rather developing the technological capability to read the quantum information patterns that preserve perfect records of everything that has ever occurred in the universe. Through quantum archaeological techniques, the achievements of ancient advanced civilizations might be accessible not as physical artifacts, but as quantum information patterns encoded in the fundamental structure of reality itself. The quantum realm might therefore represent the most complete archaeological archive possible, where every quantum technological achievement of prehistoric civilizations remains permanently preserved in the quantum correlations that govern atomic behavior, waiting for quantum archaeologists equipped with sufficiently advanced measurement techniques to decode the information patterns that connect contemporary quantum systems to the ancient quantum technologies that help shape the quantum structure of modern reality. Locked within the magnetic minerals of ancient rocks lies an invisible compass that has been recording Earth's magnetic field for billions of years, and within that magnetic archive, some researchers believe they may have found evidence of artificial magnetic fields so powerful they could only have been created by advanced technological civilizations that mastered electromagnetic forces millions of years before humans discovered electricity. This paleomagnetic record represents one of Earth's most complete and continuous databases, preserving detailed information about magnetic field strength, direction, and temporal variations that span the entire history of our planet. Every volcanic eruption, every sedimentary layer, and every magnetic mineral formation has captured a snapshot of Earth's magnetic field at the moment of its creation, building an enormous archive of geomagnetic information that extends back to the earliest periods of planetary formation. Earth's magnetic field operates as a planetary-scale recording system that automatically preserves information about magnetic conditions in microscopic iron-bearing minerals found throughout crustal rocks. When these magnetic minerals form or cool below their Curie temperatures, they lock in the magnetic field orientation and intensity existing at that moment, creating permanent records that persist for billions of years with remarkable stability and precision. Advanced civilizations might have developed electromagnetic technologies that created artificial magnetic fields powerful enough to leave detectable signatures in this paleomagnetic record. Hypothetical prehistoric societies could have built magnetic levitation systems, electromagnetic power generation facilities, or magnetic field manipulation devices that operated on scales large enough to modify local magnetic field conditions in ways that remain detectable today. The persistence of magnetic information in stable mineral systems means that technological magnetic signatures could survive across geological timescales even after the physical devices that created them had completely disappeared. Magnetic minerals possess extraordinary recording fidelity, preserving magnetic field information with precision that rivals modern electronic storage systems, while maintaining data integrity for millions of years under normal geological conditions. The search for ancient technological magnetic signatures requires sophisticated analytical techniques that can distinguish between natural geomagnetic processes and potential artificial sources of magnetic field modification. Paleomagnetic analysis involves extracting microscopic samples from ancient rocks and measuring their magnetic properties using ultra-sensitive magnetometers that can detect magnetic field variations measured in nanoteslas. Some magnetic anomalies discovered in ancient rock formations display characteristics that challenge conventional understanding of natural geomagnetic processes. Unusual magnetic orientations that don't match expected paleomagnetic directions, artificial-looking magnetic patterns that appear too regular to result from natural processes, and magnetic mineral concentrations that suggest technological rather than geological origins have sparked intense scientific debate about their possible causes. These magnetic mysteries appear in locations where geological conditions should produce predictable paleomagnetic signatures according to established models of Earth's magnetic field behavior. Instead, researchers occasionally encounter magnetic patterns that seem inconsistent with natural geomagnetic processes, displaying characteristics that some interpret as potential evidence of prehistoric electromagnetic technologies. Advanced magnetic technologies developed by ancient civilizations might have included electromagnetic transportation systems that levitated vehicles using artificial magnetic fields, power generation facilities that harvested energy from planetary magnetic field interactions, or communication networks that transmitted information through controlled magnetic field modulations. Such technologies could have created magnetic field disturbances powerful enough to overwhelm natural geomagnetic signals in localized regions, leaving permanent magnetic signatures that remain detectable in rocks that formed during periods of technological activity. These artificial magnetic patterns might appear as geometric arrangements of magnetic vectors, unusual magnetic intensity variations, or electromagnetic signatures that suggest deliberate manipulation rather than random natural processes. The detection of artificial magnetic signatures requires advanced magnetometer surveys that map magnetic field variations with extraordinary spatial resolution and sensitivity. Modern magnetic surveying instruments can detect magnetic field changes as small as 1 part in a billion, revealing subtle magnetic anomalies that might indicate technological rather than natural magnetic sources. Magnetic microscopy techniques allow researchers to examine magnetic properties at scales measured in micrometers, revealing microscopic magnetic patterns that might preserve evidence of ancient electromagnetic technologies. These high-resolution magnetic analysis methods can detect artificial magnetic modifications to natural mineral systems that would remain invisible to conventional paleomagnetic investigation techniques. Rock magnetic analysis provides additional tools for investigating potential technological magnetic signatures through detailed study of magnetic mineral compositions, magnetic domain structures, and magnetic recording mechanisms. These techniques can identify magnetic minerals that display properties inconsistent with natural formation processes, potentially indicating artificial modification or technological magnetic influence. Some paleomagnetic investigations have revealed magnetic mineral assemblages that appear artificially optimized for magnetic recording efficiency, displaying characteristics that suggest deliberate engineering rather than random natural selection of magnetic phases. These unusual magnetic mineral compositions might indicate prehistoric understanding of magnetic recording principles that exceeded natural geological processes. The possibility that ancient civilizations developed sophisticated understanding of electromagnetic phenomena opens theoretical possibilities for magnetic technologies that operated according to principles different from modern electromagnetic engineering. Prehistoric magnetic technologies might have utilized biological magnetic systems, quantum magnetic effects, or exotic electromagnetic phenomena that created magnetic signatures unlike anything produced by contemporary electromagnetic devices. Advanced electromagnetic technologies might have included magnetic field control systems that modified regional geomagnetic conditions for technological applications, electromagnetic manufacturing processes that required precise magnetic field manipulation, or magnetic navigation systems that relied on artificial magnetic landmarks for guidance across continental distances. These hypothetical ancient magnetic technologies could have left detectable traces in the paleomagnetic record through various mechanisms including magnetic field strength modifications, artificial magnetic reversal patterns, or electromagnetic signatures that indicate controlled magnetic field generation rather than natural geomagnetic processes. Future advances in paleomagnetic analysis techniques will likely reveal increasingly subtle magnetic signatures that could potentially indicate prehistoric electromagnetic technologies. Improved magnetic sensors, better understanding of natural geomagnetic processes, and more sophisticated magnetic modeling might uncover evidence of ancient civilizations that achieved electromagnetic mastery along pathways completely different from human technological development. The magnetic mysteries preserved in ancient rocks might therefore represent one of the most durable forms of technological evidence that advanced civilizations could leave behind. Unlike organic materials that decompose or metal artifacts that corrode, magnetic signatures remain permanently locked in stable mineral systems that preserve electromagnetic information across geological timescales. In this view, every magnetic mineral becomes a potential technological artifact, every paleomagnetic anomaly a possible communication from prehistoric civilizations that understood electromagnetic principles well enough to leave permanent magnetic messages encoded in the planetary magnetic field system that continues to record and preserve magnetic information across the vast expanses of geological time. Deep within the crystal lattices of ancient minerals, photons of light from prehistoric civilizations might still be glowing, electromagnetic radiation trapped for millions of years in mineral structures that serve as geological batteries, storing the luminous signatures of advanced technologies that once illuminated worlds we can barely imagine. This extraordinary possibility emerges from understanding that certain minerals and crystals possess the remarkable ability to trap light and electromagnetic radiation for extended periods, creating natural archives of ancient electromagnetic environments that preserve information about light sources, technological emissions, and photonic activities that occurred millions of years ago when Earth's surface bore a completely different face. Luminescence dating techniques have revealed that some minerals can store light energy for millions of years with extraordinary fidelity, maintaining photonic information in crystal defects, electron traps, and atomic-level storage sites that function like microscopic batteries charged by ancient electromagnetic radiation. These natural light storage systems demonstrate that minerals can serve as photonic archaeologists, preserving electromagnetic signatures from prehistoric environments in forms accessible to modern analytical techniques. The physics underlying this photonic preservation involves the interaction between electromagnetic radiation and crystal lattice structures at the atomic level. When high-energy photons encounter certain minerals, they can displace electrons into metastable energy states where they remain trapped for geological timescales, waiting for appropriate stimulation to release their stored energy as characteristic luminescence that carries information about the original electromagnetic source. Advanced civilizations might have developed artificial light sources, laser technologies, or sophisticated electromagnetic devices that created distinctive spectral signatures preserved in light-sensitive minerals throughout their technological territories. These prehistoric photonic technologies could have included coherent light systems for communication, high-energy laser applications for construction or manufacturing, or exotic electromagnetic devices that operated according to optical principles we haven't yet discovered. The search for ancient light signatures requires sophisticated luminescence analysis techniques that can extract photonic information from mineral samples with extraordinary precision. Thermoluminescent spectroscopy can stimulate trapped electrons to release their stored energy while analyzing the spectral characteristics of emitted light. Optically stimulated luminescence techniques use specific wavelengths to trigger photon emission while preserving information about the original electromagnetic source. These photonic archaeology methods can detect electromagnetic signatures that differ from natural solar radiation through analysis of spectral patterns, luminescence intensities, and photonic behaviors that suggest artificial rather than natural light sources. Natural sunlight displays characteristic spectral distributions that reflect solar fusion processes, while artificial light sources typically produce different spectral signatures depending on their technological generation mechanisms. Some minerals display unusual luminescence properties that challenge conventional understanding of natural electromagnetic environments. Unexpected spectral signatures that don't match known natural radiation sources, luminescence intensities that exceed predictions based on natural photon exposure, or photonic behaviors that suggest exposure to coherent rather than incoherent light sources might indicate interaction with prehistoric artificial electromagnetic systems. Certain crystal formations contain photonic signatures that appear inconsistent with natural electromagnetic environments, displaying luminescence characteristics that suggest exposure to highly organized electromagnetic radiation rather than the random photonic environments typically produced by natural sources. These unusual photonic patterns might preserve evidence of ancient laser technologies, coherent light communication systems, or sophisticated electromagnetic devices. Advanced optical technologies developed by prehistoric civilizations might have included photonic computers that processed information using light rather than electrons, electromagnetic communication networks that transmitted data through modulated coherent light beams, or exotic optical devices that manipulated electromagnetic radiation for purposes beyond current technological understanding. These hypothetical ancient photonic technologies could have created electromagnetic environments so intense and sophisticated they left permanent modifications in the optical properties of minerals exposed to their radiation. High-energy laser systems might have created characteristic damage patterns in crystal lattices that remained detectable millions of years later. Coherent light communication networks might have left distinctive spectral signatures in minerals along their transmission pathways. The investigation of photonic archaeological evidence requires advanced spectroscopic techniques that can analyze mineral optical properties at extraordinary levels of detail. Modern spectroscopy can detect electromagnetic signatures at the single photon level, revealing subtle photonic patterns that might indicate technological rather than natural electromagnetic sources. Photonic microscopy techniques allow researchers to examine light-related mineral properties at microscopic scales, revealing optical modifications that might preserve evidence of ancient electromagnetic technologies. These high-resolution optical analysis methods can detect artificial photonic signatures in individual crystal grains that would remain invisible to conventional luminescence dating techniques. Some photonic investigations have revealed mineral specimens with optical properties that appear artificially optimized for specific electromagnetic applications, displaying characteristics that suggest deliberate optical engineering rather than random natural selection of photonic properties. These unusual optical mineral compositions might indicate prehistoric understanding of photonic principles that influenced mineral formation or modification processes. The possibility that ancient civilizations achieved sophisticated mastery over electromagnetic radiation opens theoretical possibilities for photonic technologies that operated according to optical principles different from modern laser and fiber optic systems. Prehistoric photonic technologies might have utilized biological light generation, quantum optical effects, or exotic electromagnetic phenomena that created photonic signatures unlike anything produced by contemporary optical devices. Advanced electromagnetic civilizations might have developed optical manufacturing processes that required precise control over coherent light sources, photonic navigation systems that used artificial electromagnetic beacons for guidance, or optical information storage systems that encoded data directly into crystal lattice structures through controlled electromagnetic modification. Future advances in photonic archaeology techniques will likely reveal increasingly subtle electromagnetic signatures that could potentially indicate prehistoric optical technologies. Improved spectroscopic sensitivity, better understanding of natural electromagnetic processes, and more sophisticated optical modeling might uncover evidence of ancient civilizations that achieved photonic mastery along pathways completely different from human optical technology development. The light trapped in ancient stones might therefore represent one of the most exotic forms of technological evidence that advanced civilizations could preserve across geological time. Unlike physical artifacts that decay or chemical signatures that disperse, Photonic information stored in mineral lattices could maintain electromagnetic records of ancient technological activities with precision that rivals modern optical storage systems. In this view, every luminescent mineral becomes a potential photonic artifact, every unusual spectral signature a possible communication from prehistoric civilizations that understood electromagnetic radiation well enough to encode their technological achievements in the photonic properties of crystals that continue to glow with ancient light across the vast expanses of geological time. These mineral light repositories might contain not just evidence of ancient optical technologies, but actual information encoded in photonic patterns that preserve technological knowledge, communication messages, or even consciousness patterns from advanced civilizations that achieved such sophisticated understanding of electromagnetic radiation that they could store their entire technological heritage in the luminescent properties of crystalline light storage systems.